So this lecture I am not going the whole lecture. I only go through some of the important points about OFET and a few example and applications. After that, I will break the session into off. We will go through some of the tutorial questions about how to determine the efficiency of solar cell, because I talked to everyone in the first tutorial. You will very well understand how to calculate band gap and CV and all. Like that, at least for one device, how to calculate efficiency and to understand how the photovoltaic characteristics, how to determine. So that will be one of the important, since you are attending organic electronics, at least for one device, you should know that one device you know the complete characterization. Okay, in this whole GIAN course we already seen all these things. Now we are in OFET. These two sessions we are going through tomorrow, OLED and interface engineering of organic semiconductor. Okay, so this slide I show that when you study about photophysics, in this one I didn't go through much OFET, this one. That's why I thought of telling different lecture about this one. We have gone through all those things, but again for photophysics of organic semiconductor we use OFET mainly to calculate mobility of the material. I think I already explained how important the mobility for charge transport and charge extraction in the OPV device. The same way the mobility important in OLED device also. So in organic semiconductor we use OFET to derive the mobility. So mobility, as I explained, is a velocity of charge carrier under electric field. If you see the velocity divided by electric field, the velocity is now the centimeter per second, and electric field we can define as voltage by distance. We see that the unit is centimeter squared per volt and per second. And as I said, this how we can understand the OFET means. So this is like used as a switching device. Okay, you can how to make on and off state. So this slide is also already gone through. If you want to explain the gate voltage, how much gate voltage applying, according to that you can control the output characteristics. If you increase the gate voltage, the gate voltage, the linear curve is keep on increasing and the output is varying. Okay, so here when you apply this gate voltage, it will create a conducting channel between source to drain. So according to how much field you are creating, according to the conductivity is increasing. So how this in tap water, how we can control the flow of the tap water by adjusting your gate knob. So if you open completely, you can get a high flow. If you open less, it will flow less. The similar analogy you can use it to understand the OFET. Okay, so here the distance is called W, and that's a width and length. L is a length, and this is a width of the channel. Okay, you can understand. Okay, now I am giving a little bit what is it. So here we can do two. If you see this output characteristics, we can see the two regions. One is there is a variation linearly. This is a voltage from source and drain. You can see depends on your gate voltage. There is a linear. After that, it will become saturated. So all this portion is called a linear region. This is saturated region. So from this two region, we can calculate the mobility. If you take VD is small, so means until this region, your drain voltage is small. After that, it will become bigger. If you consider this linear region, you have to take this mobility W by L and see that if it is greater than Bg means when suppose if you have minus 10 voltage, your 10 voltage is here like this. If it is beyond that one, then you have to use this equation 2 to find out the mobility of this one. So this figure will tell you about how this, in this one, if you have for example, if you have this 20 volt, after the 20 volt, that means your VD is drain voltage is greater than the gate voltage. There is almost channel is not conducting saturated point. That means your gate is pinched off. We don't have enough passage to go through. That's the maximum amount it can go, right? So that's called your that critical point, actually pinch off. So this is a maximum. We use this formula to calculate the mobility of the things. Okay. For example, you got to understand in OPV and OLED device. For example, OLED, we do the charge injection. The charge injection we can do it at 1 or 2 volt. So if you feel this electric field is voltage by divide, when you use you are applying the gate voltage, then we can see the output current is increasing fast. As soon as the gate voltage becomes 0, then there is no current conduction. So this is a case when you are applying no voltage, but when you apply the gate voltage, you see is pushing the charge on the channel. Once the charge is built up here, it will start conducting. So this is a simple understanding of how this OFET is working. Just as giving the field to conduct, create a conductive channel to the current pass through from source and drain. Okay. So now you understand how this OFET is working, and again this OFET performance is based on how these molecules are arranged, in particularly for organic semiconductor. For example, if the molecules are very ordered way, this is the same molecular layer, we are getting the very low, very high mobility of 0.6 centimeter square. When you have the zigzag arrangement, then your mobility is going to 10 power minus 6. Even if it is more disordered way, it's even very, very less, 10 power minus 19. Okay, you have to understand for molecular semiconductor, the mobility depends on how much is a molecular ordering. Okay, but as far as crystallinity, if your crystallinity is more, you will get a high mobility. Okay, so next thing is, and also not only things, and also how much the grain boundary is forming. If it is highly full crystalline, we have good mobility. According to how much grain boundary is increasing, then it will affect the mobility. Suppose if they measure the mobility is within 1 grain, the mobility is not 1 centimeter square. If you have a lot of grain boundaries, then it's increased little bit amount. If you go according to that, because the grain boundary is just as restricting the charge flow path between source and drain. Okay, this node. So this is just will tell you that what is the difference between the OFET charge transport and other devices what we are using OLED and OFET. So here is source and drain is make it horizontal. It's a horizontal transport, and other devices is cathode and anode is on 1 by 1 and is a layer structure, so that is in vertical transport is happening. Okay, so here usually the mobility calculated from here in the transistor may be little bit higher than the mobility calculated from the other method like SCLC or time of flight method. Okay. Okay. So this is some of the example of P3ST PCBM and TIPS BSc, how the mobility is varying and all those things. I think this also I have shown this example in my previous lecture. I'm just so that how this OFET can be used to measure the mobility. And the other thing is transistor characteristics for P3ST. Another one. This P3ST we make a device on SiO2 and AES contact. So here we found that the mobility of this device is 0.12. Okay, the P3ST material. Okay. So this is a IV curve for the P3ST transistor. And this is another material. Is a hexabenzopyridine. It has a very flat molecule. It is preferably having the structure of this type of here we have a side this here is lying is perpendicular to this surface. We can have this type of rod-like structure can form on the things. So when you form this line, you can see the very nice arrangements, because this is a very flat molecule. It can nicely arrange 1 by 1 like this. So in this molecule, the field effect is it preferably is end on means it will arrange in vertically like this in like end on conditions, because this is flat. So the substrate is around here. This is end on configurations. Okay. So in this one, the mobility of this material is given here. The variation of the output characteristics of this material is given, varying with a different voltage up to minus 20 to minus 40 volt. Okay, this OFET characteristics for HPC molecule. And other one I can show that some of the other applications. We can also use this OFET for organic field effect transistor like this one. Organic detecting light. We can make a OFET like this by applying the light on fall on like this. We can also generate the photocurrent on this. It will also use to detect any photons, this structure. Okay. Another thing is we can also use the OFET as a sensing device as well. Like this, I can talk on for many applications. The main thing is we apply any charge inject, apply any voltage in gate. The switching operation is start here. Okay. So in this one, what they do is the same OFET structure. They use a different dielectric constant like polystyrene, PVA, and PMMA and PVP. Then they use the OFET to detect the ammonia gas. So with the different dielectric value, they can got different switching conditions. If you say that with a different time, with the green color is called PMMA dielectric, and PVA is the dotted line. And so it looks like when you have used the PVA type things, we have the sensing capacity is very higher in this case. So with these slides, I think I will give some good example about where is the application we can use. I can go and I'll talk about each example, but basically everything is same device structure and same application to find out the mobility only. And different materials we can talk about different value of mobility come. Okay, so you understand this mobility is only to find out the mobility can be extracted from this OFET device, and some of the switching device application we can use it. So one of the real application I can show you that in OLED device. So tomorrow we are going to talk about organic LED. In organic LED, how the different color, how we are getting different. Basically in our LEDs we use only 3 color. Maybe you may get some idea from previous lecture. Red, green, blue. Based on this 3 configuration only we can get the color output, right? So how do you address these 3 LEDs? Because they don't. Because different color. So normally we use OFET. We have different pixel like this. We have the like this data lines. Source and drain will be there. The data line will decide which pixels to light up. So to like transistor when you use up and 0 1, right? Like this OFET can be used together with the OLED device to write which LED to light up. You all if you studied about digital electronics, you know that if you have 2 lines 0 and 1s, there will be 4 different combinations 0 0 0 1 1 0 and 1 1. Like this, the pixel also learned it. By addressing this pixel, we can light up them according to what these are all everything's programming in different way to light up how much which LED could light up, which current pass through. It will be decided by the data line. Okay, so we will go through this one in tomorrow OLED sessions. I'm just saying that where is OFET used in real application. Okay, so with this one I will just finish this OFET lecture. Then we'll see some of the go through the some tutorial on this one. Okay, if you have any questions, and ask me right now. So any question? Yes. Sorry? Yeah, it's higher. That's why I said the comparison slide. So this transport is on this transport is horizontal, this is vertical. When you have a horizontal channel, it will easily transport, but vertical, because organic semiconductor is such a way that it light off, it's not fully conductor like metal, it's particularly insulator. According to thickness, the conductivity is vary. But in the channel, it won't go. It can even surface travel. It just depends on everything is same. Even the top one layer, it can travel the mobility. So this is because of this channeling only makes difference. Little, not completely, a little bit higher than one. Okay. So before go through the next tutorial, you just remember this, how the efficiency calculations. The efficiency as said is how much electron we are power out and power in. Here the P light is input, that's photon input, and we are getting the how much electron out. So the electron output is calculated from VOC, JSC and FF, and input light. Normally the P light is under 1 sun, okay. So this everything is about, anything is divide, multiply voltage and current is nothing but power you will get, okay. So the input light also in power, this will calculate in so the power is given in watt per centimeter square. This is also watt, but both are in watt. So EQV we are not doing, but just remember these two equations. And fill factor is calculated. You see this from here. This is short circuit current and this is VOC. And in this, if in this JV curve, somewhere the point is the multiplication of JSC and V somewhere is maximum. This will be the maximum point. If you take this is the maximum point, its corresponding voltage is corresponding voltage is a VMPP, and this is JMPP. Because this is y-axis is a current, JMPP. Okay. So using that VMPP, JMPP, and outside one, we'll get fill factor. So fill factor is just saying that how square. This maximum PowerPoint only tell that how much, what is the maximum square can form within this JV curve. That is your fill factor, because we can divide the maximum square by the small square by the outer maximum square, we will get some ratio. That's your fill factor. Ideally, we want to have the curve like this. Fill factor should be 1, but no device give the 100% fill factor. Okay. So note down these things. We go through this some of the question. Get verified. No, I just put verified. I need to open first.
Okay. Now is third screen is actually showing. That is the problem.
Yes, I'll go first. What is F5?
Actually, not only F5. F5 is this one. No, not this one.
I know this, the PowerPoint we can do, but this one. Display.
It's a touch screen also?
Yeah, touch screen. Yeah, this touch screen. Why?
I think this is showing plus screen.
Just to put control or function.
That is really
The other days came. Display, you go to things, right click. Display system. 2, you select 2. Detect.
yeah. Display 2 is actually showing the display here. The one only actually your screen. Okay. We have to duplicate this space.
Yeah, now it's done.
Yeah.
Okay, can you see that first one is very direct question. Can you do that? Huh? What is it? Yeah, I got the 2. What is the PC? There are two questions here. Yeah, that's just one. Yeah. Because 1 cent is equal to 1000 watts per centimeter squared. The power input, you just take it as a 1, the denominator. Okay. So just take 1 cent. The P in power in. So you want to calculate one thing. Yeah, just to the numerator we call denominator just to put 1 because these are all calculated under 1 cent. If you do the first ones correct, this is just a multiplication only. Just to use the formula which I gave you in the slide. So first you have to write down the formula, then you can find out. PC. There are 2 questions here. 2134. Yeah, that's right. 6120. 60. Yeah, that's right. You had 16%. Where do you get MPPG? Yeah. So you just follow the previous slide. I showed that what is fill factor and PC. The Pn is just 1. What is 16? Wait, this first you write a formula, then only you get correct. That you didn't note on the formula.
Yeah, I didn't know the formula. I calculated. I don't want to see it.
Yeah, okay. No, if you don't know the formula, then I can tell you again. You did. So, okay. I think some of you forgot to note the formula. I will tell you again. Just write down. I told you. Yeah, at least you note this. This is a formula PCE and fill factor. These two things you note down, please. What are known is that is 100 milliwatt per centimeter square. You don't worry, you just leave it one. Only take out only the bottom. Yeah. 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 Which question are they? Yeah, you got to use this one. Filter, yeah. I asked filter. I use this one. I already given what is yeah. 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 Yeah, you already have the fill factor value. Yeah. Initially calculated. No, you need no need, just you don't understand what is it? Yeah. So what is PC? First I said PC, right? Calculate PC. Calculate the power quantity efficiency if, so the first question. Yeah. What do you got? 1620. Yeah, that's right. 1620.
If you multiply with this value, you're saying 0.7 is getting cancelled.
No, the PC I said like this, right? I said PN just 1. This value VOC.
VOC is 0.90.
Yeah, 0.90 times 25 times. No, where is 10 power minus 3?
Milliamps.
No, you just take the number. Why you want to convert minus 3?
Okay.
You just keep it 0.74. Divided by 1. What is it? Don't take milliamp. Just everything we keep it in the milliamp. So when you calculate this one, don't convert anything is milliamp. Just to take the value as it is, because these are milliampere centimeter square. Your input power are also 1000 milliwatt per centimeter square. Okay. If it is 1000 watt per meter square, you can take it as 100 milliwatt per centimeter square. So don't convert any value into 10 power minus 3 or something. Take the value and just calculate. Okay. Where is the problem? Convert பண்ணுங்க. Don't convert it. Just multiply. Because we are keeping the denominator value is same, milliampere per centimeters. So just to substitute the value and find out. Yeah, this is right. Yeah, that's right. What is it? What's the value? What's the answer? How you got 0.0? No, the first question is PCE. What is the PCE? Power conversion efficiency. That's the first question. Yeah, P just take it 1. Just multiply all those things. Yeah, P out, that's why you write PJ.
இது மட்டும் மல்டிப்ளை பண்றதுனால
Yeah, just multiply all those values. How much you get?
another 16.65.
Yeah, multiply DOC, multiply fill factor.
0.74 into 25 into 0.90.
Yeah, that's answer. Divide by, because how the down is 1. Yeah. That's the first question. Okay. So now you know the P in, then you find out what is the fill factor. I asked second question, what is VMPP? So sorry, JMPP. You know what is fill factor? You know what is VOC, GOC? You know VOC are given. You know the fill factor now. Then you can find out, just rearrange. Right, all the amount out of 5, you know the 4 value you can find. No, not this question, this formula. Okay, this one. What is another answer? Okay, that's right. How much? You are right? Why not? This row you got it right? You are also? 16, what is the other one? 16, what is this one?
0.
No, what is this? Yeah, what is the answer?
0.2.
No, not 0.1. I'm asking the current, right? Current. How much you are getting? Yeah, 21. Guys, okay? You are not doing. Oh, you are not doing it. Okay, that's okay. So you guys know very well, right? You are sitting separately. What is your answer?
First na JMPP calculate பண்ணோம் first. 0.021.
Anyway, this okay, but anyway, you are not taking convert. You are not convert. Just answer is 25. 25. Yeah, no need convert. Just take the value. Yeah. No need convert. Yeah, just take as it is. Yeah, 25 minutes. No need. Just take as it is. What is this? Yeah, okay. The second one, okay, most of them got right. So go to, then you will get more practice. Do it one. I just put the fill factor. So you know. So this also you have to use the first PCE, because you know the PCE and JSC, VOC, and power input is just take it as 1 and calculate what is the fill factor. You use the PCE, the formula, okay. So Pn should be 1 actually. Don't convert any value, just to take the value as it is. How much are 70? Yeah.
1 1 kilowatts per meter square.
No, 1000 watt per meter square, 1 sun.
1000 watts means 1 kilowatts per meter square. That means 1000
Yeah,
watts per
yeah,
square,
1000.
meter square.
Yeah,
Okay.
1000. That's 1 sun. We calculate it as a P at 1 sun. You just put 1. Because when you put 1000 watt, we are asking milliwatt. That's why we cancel. Yeah, that's right. Everything will be cancelled out. That's why you don't worry about those things. What's the first one? A. 75, then 76, 78. What is this one? 71. Okay. Yeah, 71. Right. You got it right? 75, 76. You make it normally, we will give it 2-digit only. This should be 77, this is 71. Okay. 78 should be, this is 71. Yeah, 7576. We can give it to point 2-digit only, not 4. That's okay. 757678. 70. Okay. You are sitting alone. You're done. What's the first one? I know. First question is it?
First question is PVC and LVC.
No, just don't aim, just 25, 25 because we keep milliamps because 1000 I'm keeping below 1. Actually it is 1000 watt per meter square. When you have 3 bottom or the already cancelled, just skip number wise, okay? So don't put it, just to take 25. Okay, then it will get 16.6. Yeah. Okay. What is this one? 25, 76, 77. Yeah, right. Okay. You guys are okay? Have any problem? The first one, where is it? I didn't see the first one. First question, didn't get answer. 21 or 6. Okay, that's right. Yeah. So anyone got any problem? I'll go to the next question. If I think this is straightforward. Yeah. Huh? 1000 watt per centimeter square. Because why I'm saying that you take value as it is, the below the denominator is 1000 watt, I put just 1 sun. When you have 1000, we keep it as at the top value is milliampere. Actually, correctly we got to take ampere. When this watt I'm getting instead of 1001, that milli I'm taking just as it is, that's why it will cancel out. So we keep the value as it is, okay? You got it? You may confuse to why 1000 watt, milliwatt you are not converting. Because we are already converted 1000 watt is to 1, okay? That's why. So now the third one is, here is a one big question. Here you got to calculate the third question, the field PCE for 3. If it is 1 sun, what should be the PCE? If it is 0.7 sun, what is the PCE? If it is 0.5 sun, now you got to consider your denominator as well, okay? The PCE normally calculated according to the 1 sun condition. If you have 0.7 means the PCE will vary, okay? You got to take it denominator. You got to use the equation now. Any question? No, when you use milliampere, just to keep 1 only, you would 1. If it is 0.7, you keep 0.7, okay? Keep the value.
Stands for solar constant, right?
No, the input power is supposed to be 1000 watt per centimeter square. Okay, 1000 watt. Not 1000 watt per meter square. Everything is standard.
I think it's 1361.
Huh?
1361 per meter square.
1300, no. No, this is one.
It's 1000.
Yeah, 1 cent is 1000 watt per meter square, 100 watt per centimeter square. You can, for if you want to convert centimeter. Okay. Okay. Yeah. I'll be giving the fill factor, don't confuse, I'm giving the fill factor is 55, that percentage you have to calculate 0.55. Okay. Yeah, take it as a fraction, okay. Yes, it percentage. When the percentage you calculate, particularly put in the percentage, you remember you have to take it as 0.55, but previous case you use, okay. When you take a calculation, you need a percentage means you have a 0.55. So I specifically put percentage bracket, you got to take it in consideration, okay. Yeah, yes. Any question? No, you take 1 as 1 you have to calculate, then second time you go to calculate same value divided by 0.7. You just use value as it is. For 1 row you have to calculate 3, I think 1.7 and 0.5, okay. Okay. There will be 3 different PC you will get, okay, for. Got it? Thinking? It's okay? Working fill factor 1.3. No, fill factor, where is the formula? You didn't write down the formula. That is PC. That is PC. What is fill factor? No, the fill factor is this one. First question.
Second.
What is the first one?
Then
6.4. Yeah, 6 point. Yeah. So if you remember my lecture in previously, huh? No, this is okay, but what is the fourth question? Just to give, if you don't, yeah, if you understand, yeah, what? Yeah, the straightforward answer. If you understand, then you can answer. Yeah, why bulk heterojunction?
When you have heterojunction, they may not mix properly.
Junction area, the surface area will be much more, and the size of the grain size will be less than the mean free path.
Mean free path. There is one more term I am expecting. Anyone remember? Yeah, that's closely right. There is exactly I said. Yes, correct. Diffusion length. Because the question 4 is I said diffusion length of exciton is very limited. That's why we need to have a bulk heterojunction. That's the main concept. You got? You need another diffusion length. Diffusion length of, because once exciton is created, it should go through the heterojunction, the donor junction, to get separated. It has a specific diffusion length. So the diffusion length, if it 10 to 1500 nanometer means the heterojunction should be there within 15-20 nanometers. That's the main thing. That's why bulk heterojunction only you can make this much. Because when the nanometer is like at the bottom, the below the figure it shows that is 30 nanometer. That only can create bulk heterojunction, can give the exciton can reach the heterojunction within 30 nanometer. Okay. If you understand this one, then you can understand what is question 5. Question 5, I give the two figure. I think most of you know that which one is a preferred one. And also you have to say that I have gone through many method, many technique for fine tuning the morphology. You have to write down at least 3 of the things. Any 3 method do you remember? Anyone can tell me, anyone remember the method to make the technique we use to make bulk heterojunction efficient? Solvent vapor one option, then what is the next one? Don't say English, someone. Huh? Solid additive, okay, I can take. What's the other one this side? We discussed many techniques right in the morning. And yesterday and today. Solvent additive, solid additive you said solvent annealing, then what is one more? Yeah, okay, we can also take thermal annealing as well. There are a few techniques. One is, yes? Binary blend itself don't give the bulk heterojunctions. Once you make a film, we are discussing some 6, 7. One is solvent choice. If you don't know, I will repeat it. One is choice of solvent. I said, sorry? Thermal annealing, yeah. Someone said thermal annealing. And solvent annealing, solvent vapor annealing, and volatile additives, that also the liquid additives and the solid additives, okay. So these are all different things, okay. Okay, we will we'll finish this session here already 3:10. If any we have time, we'll go through some other question tomorrow, okay. Yes. Huh? What IPC? What? Yeah. UK. Yeah. Can you explain what UK? No, that one we need to give separate experiment, not directly from this one. We have to give each and every wavelength and calculate EQ. For one wavelength, what is the current we are getting like this? Yes. EQ. Yeah, they use it. Thank you. Yeah. That's not a, we'll see maybe one, that one, okay.